The first thing we'll do to get started with the Trebuchet model is to set the graphics area and the units. We'll click on View, Numbers and Units, and we'll change the units to English pounds. We'll click on View again, and then we'll click on View Size, and we'll set the size to 50 inches. And then the last thing we'll do is we'll click on View again, and we'll click on Workspace, and we'll turn on rulers, grid lines, and XY axes. This will help us while we're creating the geometry, as we can use these intersecting grid points and also the rulers on the side to help size our objects. Next, we're going to start creating the geometry. As we start creating the geometry, we'll be paying close attention to the ruler on the y-axis, the ruler on the x-axis, as well as our origin right here. These will be useful tools for positioning our geometry. The other thing we're going to pay attention to is the readout down here. As we move the mouse across, you can see that there's an X and a Y coordinate readout for the mouse position. As we click on these different object tools, this readout will now include, for example, if we click on a rectangle, it'll show an H for the height, a W for the width, and then a theta for the orientation of the body. So we're going to be using all of these different tools to help us create these bodies. Over here we have our object palette. We have some different objects here, such as a circle, polygon, rectangle, a square, curved polygon, and an anchor. And we can anchor things to the background to fix them in space. So we'll click on the rectangle tool, and then we're going to come over here. Notice the cursor has changed, and I'm watching the ruler on the bottom of the screen on the x-axis here. And I'm going to move to a position of x equals -8, and I'm going to hover over this solid line, which is equivalent to y0. I'm going to click the mouse once, release the button, and then drag it to the other side to the +8. And y is arbitrary at this point. It really doesn't matter. This is just simply going to be anchored to the background. So I'll just find some arbitrary thickness right there and click. Notice that with our object selected here, it's showing us down here the height, the width, and the current orientation. So we've created a base that was 0.75 inches in thickness or height and 16 inches in width. The next thing we're going to do is create the vertical post that will be positioned right here. Again, we'll click on the rectangle tool, and then we'll come over to some arbitrary position. It really doesn't matter because we can join these bodies when we create the constraints, or we can also drag them around with the mouse after we're done creating them. So I just clicked at some position, and I'm watching the coordinate readout on the bottom, specifically the H value. Right there, I'm at H equal 8 inches and a width of 0.25. So I'm going to leave it at 8 and 0.5. So I made it a little bit thicker. I'll click the mouse, and now I have my vertical post. And I can click, hold the mouse, and drag these bodies around. And I'm going to move it right over the X0 position and release the mouse. And that's right where I want to position that vertical post. The last thing we're going to do is draw the beam in here. Again, click on the rectangle tool, click at some arbitrary position, and I'm watching the W readout down on the bottom left corner. I'm interested in getting this at 12 inches. The height, again, arbitrary. I'll leave it at 0.5 and click. So there overall I have a 12-inch beam right there. We can click and drag this body up. And there's a couple different ways that we can position these bodies. One is to just move them into position with the mouse. Notice how it's using the grid snap to position the body. And the other way is to create these constraints and then join them, the two bodies, while we create the constraints. Now, we still have a few more objects to create to our trebuchet here, but let's get these bodies positioned right here where they need to be positioned. So these bodies are positioned correctly. We simply use the mouse to drag them into position. That was simple enough. And this body we want to join to the top of this post. Right now, if we run it, we notice that everything is just falling with gravity. Okay, so what we can do is we can click on the anchor tool, and then we can click on this base plate right here. We'll just click anywhere on the plate. I'll click on the bottom center. And then for this vertical post right here, we could also add an anchor tool if we wanted to, but we're not able to determine reaction loads with using meters at anchors. So if you are desiring to determine the reaction force at the base right here of this post, then what you'd want to do is use a rigid joint and rigidly join it either to the background or to this base part right here. The last thing we'll do is we'll pin the beam to the top of the post. What we can do is, if the bodies are already in position, for example, if these two bodies were positioned right at that location, I could simply click on the constraint and then click right here where I want to put that pin. And then the bodies are already assembled at that location. However, if I have a body that's off in space somewhere, and I want to join them at a particular location, and it might not be easy enough to use the grid or body snap tools to get the body into position correctly where I want it, I can use these element tools. These are point elements. So I can create one element on one body and another element on the other body, and then I can use the join feature right here, which will become active once we create these elements. So these elements right here are the subcomponents that make up our formal constraints. As you can see, the shapes are identical to what we have down here. So for example, we can click on, or double click. If we double click, it'll stay in this mode until we select the arrow tool to exit the mode. So we'll double click the point element, and then we'll come over and we'll click somewhere, say on the bottom center of the beam, and then we'll come over and click on the top center of the post. Click on the arrow tool to exit that mode, and then we can just simply click, hold the mouse, and drag a pick box. So I'm highlighting these 2 points. The other way to do it is to hold down the shift key and select the points individually. Notice with those 2 points selected, the join tool has become active here. So if I click on join, it joins those 2 bodies together. If I click, hold my mouse, and drag these parts, I can see that they're constrained properly where I wanted them to be constrained. Now we'll add the remaining components of the trebuchet. Those are going to be the counterweight that we're going to put on the end here. We'll have a payload, and then we'll be connecting the beam to the payload with a rope. So let's start by creating the counterweight. So for simplicity, I'm just going to create a circle here and draw a circle of some arbitrary size. It really doesn't matter the exact size. What we're more interested in is controlling the mass of the counterweight. So we've just created a simple circle right there, and then we'll create another circle to represent the payload. This can also be of arbitrary size. Again, we're going to control the mass. We're not real concerned with the exact geometric size of it. And then what we can do is we can click on the rope tool down here, and then we'll click on the end of the beam. Notice how the snap point wakes up at the end center of the beam. I'll click once, and I'm not holding the mouse button down. I just released the mouse, and I can drag this around, and then notice it'll wake up the next snap point on the center of our payload, and then click, and there's our rope. So these are constrained right here, the way we're interested in constraining them. The other thing we need to do is we want to make sure that this body right here rests on the surface of this plate. By default, bodies are set to collide in interactive physics. Sometimes that's what we want, other times that is not what we want. For example, if this beam spins around, one side of the beam is going to collide with this post right here. And perhaps we want this to spin all the way through. We're working in a two-dimensional field right here. So in reality, this post has a cutout, and so this beam can swing through that post or through the post structure. So what we're going to do is we're going to click on World, Preferences, and we're going to uncheck Objects Do Not Collide by default. Or excuse me, we're going to check this option here for Objects Do Not Collide. It gives us a warning. That's okay. And then what we need to do now, we can still have collision, but we need to tell the software which bodies we expect to collide. So we can click on the circle, hold the Shift key down, click on the base plate, and then click on Object, Collide. So now these two bodies will collide, but the beam will not collide with the post here. The next thing we need to do is we need to constrain the payload to the end of the beam. Just like we did in creating point elements and then joining those two elements to create the pin constraint, because our payload is positioned off in space here, we're going to use the point elements and then use the join to let the program assemble the bodies. So we'll double click the point element tool, or in this case we can simply double click the rigid point element because we don't need this body to spin. We just simply want to fix it to the end of the beam. So we can hover the mouse over the end center of the beam and click once. Hover the mouse over the center of the counterweight and click, and there's our 2 points. Click the arrow tool to exit that point creation mode. Just like we did for this pin constraint here, click, hold the mouse, drag a window so we're selecting both those points. As soon as we got both of those points selected, notice that the join option here became active. Click on join, and now our payload is connected to the beam. Now, before we simulate it, I noticed before when we dropped these components just with gravity, it had a fast animation playback rate. We can slow that down. If we click on World, Accuracy, we can change the animation step right here to something smaller, maybe 0.001. Notice that'll also increase the number of frames per second that we're seeing in the playback. So now when we select our Run button, we can see that we have somewhat of a trebuchet starting here. I'll right mouse click to access the View command window here so I can pan the model down a little bit. Right click again, exit this mode. I'll click on the playback slider. Notice how the beam does not collide with the vertical post, and neither does the counterweight. However, our payload does make contact with the base plate here. In reality, there's going to be a guide slot in a trebuchet, but because we're in the 2D realm here, we don't need that body in here. We just simply represent it as a contact. As you're probably aware, there are different things that we can control in a trebuchet design to achieve the optimum throw. Those being the position of the fulcrum here, the initial starting angle of the beam, the mass of the counterweight, the mass of the payload, and also the length of the rope. What we're going to do next is we're going to show you how to create interactive controls that allow the user to change these different variables from one simulation to the next. What we're going to do first is we're going to create a control that allows the user to change the position of this fulcrum point right here. So what we'll do is we'll right mouse click or double click this point right here for the constraint, this pin constraint, and it brings up the properties window. And we can see the 2 point elements that we created earlier. These are the points that make up that constraint. What we're going to do is we're going to parameterize one of them. One of the points is attached to the body, this beam body here. The other is attached to the post. So what we can do is we can identify the first point in here, 0.8, and we'll create a parameterization for its position. From the drop-down, we'll select 0.8. With that point selected in the Properties window, we'll come up and click on Define, New Control, Offset. So it's created 2 sliders here that allow us to control the X and Y positions of that point. We're not interested in the Y offset, so we'll just simply select that, press the Delete key, and we're left with the X. Notice that it assigns an input ID to this slider called Input 19. That's useful for creating different slider controls and associating them with different features and elements inside of interactive physics. So if we right click, or now we can single click because this properties window is already open, notice how 0.8 now shows that the X position is controlled by this input slider right here. Now what we'll do is we'll define the upper and lower bounds for this offset. We can select the offset control slider. Notice how the min and max are showing right here. By default, they're always going to be 0 and 1. And we'll leave the minimum at 0, and we'll set the maximum at 4, and then we'll set the number of steps to 8. So now if we come over here and we click and drag the slider, we can see that it moves our beam across the top of that post correctly. Next, we'll create a control that allows us to have control over the orientation of the beam. Single click on the beam so that it's highlighted. Click on Define, New Control, Initial Rotation. Just like we did for the offset, we're going to set the upper and lower bounds for this control. Notice if your Properties window is already open and then you click on different objects in interactive physics, the Properties window will reflect whichever body or element you're selecting. So if we just single click on the slider for the rotation, notice how the minimum is 0, the maximum is 6.28. We're going to change this to 45, and then we're going to set the number of increments to 9 so that it snaps in increments of 5 degrees. So now if we move this, we can control the initial orientation of the beam. Next, we'll go ahead and we'll create mass control sliders for both the counterweight and the payload. Simple enough, we just select the body, click on Define, New Control, Mass. Just like we did for the offset and the rotation, we can set the upper and lower bounds. Over here we can see that we have a minimum value of 0.00045. For a mass control, you typically want to have a finite mass. It's not good to have a mass of 0. So although this is extremely negligible and we know that in the physical world we're not going to be using a mass of 0, we'll leave it at some finite value simply to accommodate the solver in interactive physics. For the maximum value, we'll define 20, and then we'll use 20 incremental points right here for the snaps. We'll click on the payload, define, new control, mass, and now we have the payload mass, and we'll set that to a minimum value of what's showing right here, just so that it's some finite value and not completely 0, and a maximum value of 2 pounds. And we'll increment this in 4 increments or 4 snaps, so half-pound increments, as we can see when we drag. If you want to see where these mass controls get applied, if we just click on the payload the counterweight, for example, we can see in the mass field right here that the ID for this control slider is assigned to the mass. So these are ways that these controls and sliders are associated with the different elements and bodies. Also, if I click on this beam right here, I can see that input 20, which is this rotation slider here, is associated with the orientation. So it's a great way to set up variables for different things in interactive physics. The last thing we'll do is create a parametric slider control for the length of the rope. Simply click the rope, click on Define, New Control, and click on Rest Length. Click on the control slider, and in the properties you'll see the properties for this rest length or the rope length slider. We're going to set the minimum value to 1, the maximum value to 10, and we'll increment in snaps of 9. So now if we click the slider and drag it, we can see that our rope changes its length. What we can do is if we drag this to its extreme, to 10 inches here, notice how we see slack in the rope. That's okay. We can just click on this body right here and hold the mouse and then drag it to its initial position. And that might change again if we change the rotation. Let's say we start at 45 degrees. Again, we're starting with some slack. Easy enough, just click the body, drag it back to its starting position right there. Now what we're going to do is run the simulation and see how things look. So we can zoom out on the model here. To do that, we can either right mouse click and use the controls here, or we can use the controls up on our view toolbar, or we can click on the graphics area, and I like to roll my scroll button on my mouse. Now we might need to set some initial values for our payload and our mass here, and also the fulcrum position. So let's go ahead and set the fulcrum position to something like that. And then we'll set the mass of the counterweight to maybe something like 14, and then we'll leave the mass of the payload at 1.5. So if we go ahead and run the simulation, okay, so we can see the important thing here is that we don't have pieces that are falling apart. We do have a proper throw starting for the trebuchet. Now what we'll need to do next is we'll need to define when the rope releases. Now in this simplified example of a trebuchet, we don't have a ring connector which allows the rope to slide off of the end of the beam. We could probably spend some time modeling something a little more intricate than what we have, but we're going to keep it simple for this example. And how we're going to control that release is going to be based off of the simulation time. So, for example, what we can do is we can click on Measure and click on Time, and we'll create a meter for time. Now let's go ahead and let's run the simulation, and then we'll stop it. We'll grab the playback slider, and we'll move it to some position. Let's increment it, and I'm clicking the arrow tool on the right to increment it slowly. And let's say, for example, we want it to release right at this position, which is time equal to 0.397. So what we want is we want the rope to be active for all time less than 0.397. So we can click on the rope. Oh, we have to reset our simulation first. Click on the rope, and let's uncheck the always for the active when field. And we'll type in time less than 0.397. So the rope is going to be active for all time less than 0.397. As a side note, this active when works for several different elements in here, for springs and forces and constraints. It's a great way to activate and deactivate different elements in the model based on different conditions or criteria. So let's go ahead and let's run our simulation and check our result. Okay, and I'm going to stop it. So we can see that the rope did release when that time was achieved, or when it exceeded 0.397. So for your example, it might take a little bit of modification to get the rope to release exactly where you want it. Again, this is a simplified version of the trebuchet in releasing this rope. But what we can do to take it one step further and simplify it a little bit more is create a control or an interactive box that allows us just to type in the value of time at which we want to deactivate the rope. To do that, just click on the background so that no other object is selected right now. Click on Define, New Control, and Generic Control. Notice in the Properties window, the type of this is a slider control. Let's go ahead and let's check the text box option for this. Notice how this changed to a box that we can just simply type in a value to. Notice also that the ID of this box is 25. That's going to be useful because what we're going to do next is click on the rope, and then down here, instead of 0.397, I'll just tag that with my mouse and press the delete key. I'm going to type in input, begin bracket, 25, end bracket. So this is what our new formula looks like. So it's going to be active for any time less than what we specify in our control right here. So for example, if we enter some value in here, let's say 0.3, which is less than what we had last time, and then we run the simulation. Noticed it released quite a bit earlier than we wanted it to, but you get the idea. So we can simply change these values and rerun it, and it will automatically change that release point. Now that we've got our basic trebuchet built, let's start taking a look at some of the meters that we can create to measure some of the different physics characteristics of the model. The first thing we can do is we can create what are called vectors. Vectors are very useful for showing a visual representation of a velocity or a force or an acceleration. For example, I'll hold down the Shift key, I'll click on the beam, I'll click on the payload, deselect the rope there, and then maybe I'll click on the counterweight. With those three bodies selected, we can click on Define, Vectors, Velocity, and now when we run the simulation, and I'll stop it, notice how we have these different vectors showing us all the different velocities taking place for those different components. So this is a great way to visualize where in the simulation a velocity might be minimum or maximum. Great for visualizing tangential acceleration versus radial acceleration and things like that. The next thing we'll do is we'll create a vector for the tension in the rope. So click on the rope, click on Define, Vectors, and Total Force. And then if we run it, okay, let's stop it right there. Notice how the vectors are pretty large. They scale automatically based on the amount of force being experienced right here. So this scaling, although it's only about 2 pounds in this position, the scaling is a little bit more than what we'd like. So we can change that. If we reset the simulation, we can click on Define, Vector Lengths, and then we can change this to something much smaller, maybe 0.0005. Select OK. That looks a little bit more reasonable. So if we run this, okay. So now we've got some vectors for the tension in the rope. And we should see that when we get up to a certain point, that tension disappears because that's when our rope deactivates. And we can see it's just up at that point. It's a great way of stepping through and seeing exactly what is occurring at different points in the simulation. So we can see exactly when that rope deactivated itself. The other thing we can do is we can create these different meters. What we like to do in this example is demonstrate projectile motion. So to do that, there's a couple different things we can do. One is we can track the projectile of the body itself, or we can track the path that it's going through on the graphics area, or we could also create a meter. So first we'll start by tracking the body. So if we reset the simulation, if we haven't done already, just drag it back to the beginning, and then click on the payload, click on Window, Appearance. We could also get to this same dialog box by right-clicking the body and choosing Appearance. And then we can click on different things here like Track Connect. Track Connect will create a single line representation of our body. So we can see that profile right there. If we go back to that Properties box, or Appearance, excuse me, uncheck the Track Connect and select the Track Outline, this will track the entire body geometry through the simulation. Okay, and it's based off of the number of track frames that we have set. And we can see it gets a little bit cloudy here because we have vectors turned on. So we could also turn the vectors off so we just see the geometry. But what we can do is we can click on the World Tracking, and we can tell it how often we want it to update these frames. So for example, if we say every 16 frames, let's reset and let's run it. We don't get as many of those objects showing up, so it's a little less cluttered there. Still a great way to see what's happening throughout time. We can also choose to auto erase the track. So as soon as it starts another simulation, or as soon as we add another feature or modify something in the model, this track will disappear. We can uncheck this option, and then if we go ahead and we run it, and then maybe stop it, and then we'll just go ahead and reset. Notice how the track is still there. So if we make a change to something, for example, if we increase the mass of the payload, or maybe change the rope length here and then run it again, we can see we have two different tracks. Okay, so it's a great way to compare new versus old. So we can turn that back on. Notice how it erases the tracks. We can also create a button. So we can define a button based off of the menu for the auto erase track. So we just simply click on the button when we want to take that data out of there, and it will erase the track. Now the other thing we talked about doing was creating different meters in here as well. So for example, let's say that we want to monitor the projectile motion or the X and Y position of the payload right here. So let's go ahead and create a meter for that. And the reason we might want to create a meter rather than track the body and just visually look at it on the screen is because, number one, this way we can see the exact XY coordinates. But number two, if we have a very long throw distance, we might have to zoom our model way out to be able to see where the object lands. This way we can keep the model at a larger view size, and we can watch what happens to the projectile path on the meter itself. So let's go ahead and let's click on the payload. We'll click on Measure, Position, and then click on Y Graph. And we'll click and drag that meter over here, and then I'll just grab the grips and enlarge it. Now, notice now we're plotting Y position versus time. What we'd like to do is we'd like to replace time with the X coordinate of the payload. So let's double click the meter. Let's tag the Y formula in here, and we'll copy that and we'll paste it over time, and then we'll replace the Y value with X, and then just simply change the label to X. Now if we look at the meter back here, we can see we're now at Y versus X. So if we go ahead and we run the simulation, we can see that projectile path right on the screen. Let's go ahead and rewind this. Now another great feature that we have here is we have the ability to retain meter values from one simulation so we can compare it to future simulations. So to do that, we can click on World, Retain Meter Values, and now when we make a change and run the next simulation, this old curve will stay on the meter here so we can compare the two results. So let's go ahead and let's just make a simple change, and maybe we'll change the payload by 1 pound. Go from 14 to 15. And then we'll go ahead and run the simulation. Okay, and I'll stop it by clicking the mouse, and we can see the comparison in just changing that payload by 1 pound. So that's a great tool there. Another thing we might want to do is set up a control to stop the simulation at a certain time. So really we're only interested in seeing how far the payload goes. Once it crosses the, once it lands at y equal to 0 here, we're not interested in seeing what happens in the negative region because that's not physically possible. So what we're going to do is we're going to define a stop control that stops the simulation when the payload crosses the 0 point back here. The criteria we'll use for stopping the simulation will be based on two things. One will say when time is greater than 0. The other will be when the payload position is less than 0. We know that when the trebuchet swings, the payload is always going to be in the positive Y region. Only when it comes and lands out here is it going to then cross and go into the negative region. And that will be some point after time equals 0. So if we want to go ahead and click on World, Pause Control, and we can define a new condition. And because we're going to try and define two criteria, we can use an AND statement. And this just tells it when both these criteria are met, this is when we're going to pause or stop the simulation. So what we need here first is we need this body information. So we need the ID for this circle. And we know that that is circle 12, and I can see that right here because That was this is the mass control for our payload. So we can say body 12, notice I use brackets around there, dot P dot Y less than 0, comma, so that was the first part of our criteria, when the body position is less than 0, and we can also say when time is greater than 0, or it could be some finite value, maybe 0.1. We know that by the time it lands it'll be well beyond 0.1 second. And then we'll end the parenthesis right here. We'll select OK, and we'll just go ahead and we'll run the simulation. And notice how it stopped exactly when the Y position crossed the 0 mark. So it's a great way where we don't have to keep rescaling these graphs, and the simulation stops by itself. So there are many other things we can look at in here in terms of the physics of the model. We can measure reaction loads and constraints. So for example, if we click on that pin joint, click on measure, we can look at the force in that constraint if we're interested in designing a trebuchet that doesn't fail. Some other things we can look at, for example, click on the payload there, and we can measure all these different characteristics. So things like kinetic energy might be important, maybe gravity potential for the payload and things like that. So a lot of different tools that we can use to see what's physically taking place with the simulation. The last thing we're going to look at is we're going to look at just cleaning up the model here, making it a little more appealing. This is great for if it's going to be saved and opened up by students, where they can just simply make some changes and look at the simulation that's already been created. So first let's take a look at the bodies. If we want to change the color of a body, you can either click the body and then click on Window, Appearance, or you can right-click on the body and the flyout menu will appear, and we can choose Appearance from that menu there. And then we can change the color to something like blue. We can show the center of mass. Notice the symbol turned on right here. We can also show the name of the body, so if we give it a custom name right here, that will show up in our show name, or in our name next to our arm right there. We can also change the color of meters, so just like we did for a body, if we right click on the meter and choose Appearance, we can change the color of that meter. We can also change the font size of different things. So for example, if we want to change the font of these sliders, click on the slider and then click on Object, Font, and change it to something like 14, and notice the size just increased right there. We can also change the actual slider size itself. So notice how these grips are showing. If we click on a grip and drag it, that can increase the size of the slider. So you don't have to work just with the default size of fonts. If you select the slider and then click on Window, Appearance, we can change the name of this, call it rope length. Okay, so that cleans it up a little bit. So you get the idea there. We can make this a little more appealing than what's showing. Now, we can also note that we can change the display of a meter. So for example, right now, if I just run this and stop it quickly, notice how I have numerical readout for this first default meter set. If I click on the arrow tool right here, it changes it to a graphical form. So I can see the graph portion of it. If I click it again, it changes it to a bar graph form. If I want to turn any of these values on or off, so for example, maybe I'm not interested in seeing X and Y, but only the magnitude of the force, I can just simply click FX and click FY, and it turns those off, so I'm only displaying the magnitude. Another great feature is the ability to save a video file of an animation. So for example, let's go ahead and run the simulation so we have results stored in memory. And then we'll reset the model. And now if we click on File, Export, we can change the export type to AVI and then select Export. And it's starting out slow here because it's writing frames out for all these different steps. But what that's going to do is that's going to save a video file of our animation. I'm just going to go ahead and stop it. That will save an AVI file that you can open up and play back. It will capture everything that's on the screen in the graphics area. It will not capture any of the tool palettes or menus. And then finally, another great feature is the ability for instructors to save this as a player-only version. So what we can do is we can click on Edit, Player Mode. Notice how all the tools went away. So we only have the ability now to move these sliders and to play the simulation. So if we save the model in this form right here, we're going to save in player-only format. We'll call it Trebuchet PO for play only. And then we'll go ahead and we'll open it up. Let's close it first and then open up Trebuchet PO. Notice I don't have the ability to go back and turn this into edit mode. This is what I have. This is a great way to keep students on task and not let them get in and to have too much fun with the software, which is very easy to do. They can only run the simulation and they can make different changes to the simulation. So this concludes the video on creating a simple trebuchet. If you have any questions, please contact Design Simulation Technologies.